Okay, on chapter 1, finishing where we left off, or starting where we left off. Temperature conversions, we talked about the temperature scales. Kelvin, Celsius, and Fahrenheit. We're going to use Celsius and Kelvin in this class. So what are the conversions? We talked about that. To go from Fahrenheit to Celsius, you take the Fahrenheit temperature, subtract 32, and divide by 1.8. To go from Celsius to Fahrenheit, you take the Celsius temperature, multiply by 1.8, and add 32. So if you did 75 degrees Celsius to Fahrenheit, if you do the conversion, you get 167 degrees Fahrenheit. Minus 10 Fahrenheit to Celsius would be minus 23 Celsius. So the Fahrenheit temperature is always going to be higher than the Celsius temperature in terms of equivalence. Kelvin scale, and we're going to use that later on in the semester, is important to scientists because it's directly related to molecular motion. So as molecular speed increases, the Kelvin temperature proportionally increases. To go from Celsius to Kelvin, you're going to add 273.15. So later on in the semester, there'll be some problems where you're given the temperature in Celsius. But to use the formula, you need the temperature in Kelvin, so you need to know how to convert it. We went over this, didn't we? I thought so. I'll go over it again. Energy is the ability to do work. And again, kinetic energy is the energy of motion. I misread my slide numbers. And potential energy is the energy of stored energy. And you know, we can categorize energy by light, heat, electrical, mechanical, and chemical are all forms of energy. One can be converted into the other. The law of conservation of energy says the energy of the universe is constant. We don't make new energy. We don't lose energy. It's just converted from one form to the other. And it's always less than 100%. And all chemical reactions involve either a gain or loss of energy. So for example, a chemical ice bag, the kind where you break the little bag inside and shake it, that reaction gains energy and absorbs energy from our skin, which is why it feels cold. Something like a firecracker goes off, releases energy. But overall in the universe, it's always constant. Go ahead. That's a good way of thinking of it. Cold always pulls energy in. Energy always flows from hot to cold. And we talked about the calorie being 4.184 joules. And 1,000 little calories is a large calorie, which is our food calorie, which is on all our nutritional information. And a chemical calorie is the amount of heat energy required to increase the temperature of 1 gram of water 1 degree Celsius. Later on, when we do thermodynamics, we'll actually look at how we do those calculations. Concentration. When we talk about concentration, we're talking about the number of particles of a substance, the mass of those particles, that are contained in a specific volume. So if you have two solutions, one is 5%, one is 10%, let's say sodium chloride, the 10% sodium chloride has twice as many sodium chloride molecules per unit volume as the 5%. And we also often use it to represent mixtures like the concentration of oxygen in air, pollen counts. You see that on TV, especially in the spring. Pollen count is high or low. Proper dose of an antibiotic. You want to give so many milligrams per kilogram. That's a concentration. Mass per unit volume. Density and specific gravity. Density is the ratio of mass to volume, and it's an intensive property, meaning it doesn't matter how much there is of the substance, it's always the same. So water's density is 1 gram per milliliter. It's the same whether I have 1 milliliter, 1,000 milliliters, an ocean of water. It's always 1 gram per milliliter. And it's used to characterize a substance, as each substance has unique density. Did we talk about Archimedes in here? Did we talk about Archimedes? Well, in ancient Greece, as the story goes, the king would, say, want a crown made. He'd give a pound of gold to a jeweler. The jeweler would go off somewhere and make a crown and come back. And the king would weigh it, and it would weigh a pound. So he had this, but he never knew if the jeweler took some of the gold out and mixed in some base metal. Couldn't tell. So then one day Archimedes went to sit in his bathtub. And what happens when you sit in the bathtub? The water goes up. And he had an aha moment. But back in ancient Greece, he yelled Eureka. Went running through the streets to the king and says, I know how we can tell. We can take the pound of gold, because it has its own density, put it in a tub of water and see how high the water goes. Then when you give it to the jeweler and he brings back the crown and it weighs a pound, regardless of the shape, when you put it in the water should go up the same level. If he mixed in a different metal, let's say lead, which was more dense, water will go up more. Or something that was less dense, it wouldn't go up as high. And that's how they would test to make sure that the jeweler used the pure gold. If the jeweler was cheating, he was fired. And back then, the severance policy was they severed your head from your neck. So density is equal to mass over volume. The units for density, we have grams per milliliter, grams per cubic centimeter, and grams per cc. And as we learned before, a cc is equivalent to a milliliter. So you should also know density is mass. So mass is equal to what? Rearrange the equation. Mass is equal to density times volume. Volume is equal to, no. What's density equal to? What's volume equal to? Volume is equal to mass divided by density. Look, just take this equation, divide each side by density. So there's the three forms in which you're going to have to use the density equation. Just did that. So there's an example. So here you have water. The cork is floating on water. And if actually you want to measure the density of the cork, you have to submerge the cork. And then you have a brass nut there on the bottom. And at the very bottom, you have liquid mercury, which is even more dense. So the mass of the brass isn't as dense as the mercury, and the cork is less dense. So if you ever go and have your fat content measured, your percent fat body mass, the right way is they stick you in a tub of water and submerge you. They actually stick you under the water and see how high the water goes. So densities of some common materials: air, ammonia, benzene, milk, rubber, turpentine, urine, water, wood. See, kerosene and gasoline are less dense than water, so oil floats on top of water. So here's an example. We have a 2 cubic centimeter sample of aluminum. It's found to weigh 5.40 grams. Calculate the density in grams per cubic centimeter and grams per milliliter. I like they saw it. Plan your trip. Starting point, we have 2 cubic centimeters weighs 5.40 grams. So density is mass over volume. We have the mass. We have the volume. Hopefully we have the answer. Oh, go back one. Just put them in the equation. 2.70 grams per cubic centimeter. It also asks grams per milliliter, and I told you a cubic centimeter is equal to a milliliter, so it's the same answer, 2.7 grams per milliliter. So that's a pretty easy calculation. Calculate the volume in milliliters of a liquid that has a density of 1.20 grams per milliliter and a mass of 5 grams. We want to know the volume. We have the density, we have the mass. Right here we know the variation volume is mass divided by density. Go back, I keep hitting the thing twice. So the mass, and this is the reciprocal of the density, so this is 1 over density. So it's mass divided by density. 4.17 mils. No? Okay, we said volume is mass over density, right? So volume is equal to grams. Density is milliliters per gram, right? If we look at that, then so it's grams over 1, which is the mass, times milliliters over grams. This is 1 over the density. So it's mass divided by density. So it's 4.17 mils. Okay, you may encounter that in the biotech field if you have to add a certain weight of material and it's a solution with a certain density. How many mils do you have to add? Or how many liters if you're in production. Air has a density of 0.0013 grams per mil. How many significant figures? 2, yes. What is the mass of a 6.0 liter sample of air? That'd be A. So if we look at A, we want mass. Let's see if I can get this to work right today. I don't want text pen. I want pen. Okay. So we said mass is equal to density times volume. So what's the density of the air? So that would be 0.0013 grams per milliliter times the volume. What's the volume? 6.0 liters, but we want the units to cancel. So I need to take the liters and do what? I need to convert it to what? Milliliters. So 6 liters, how many milliliters? Quick. 6,000. Or if I want to do it with 2 significant figures, because now I have 1. 6.0 times 10 to the third. And whatever that answer is, 7.8 grams, I'm guessing. Second one, calculate the mass in grams of 10 mils, should be of mercury, if the density is 13.6 grams per mil. Same problem. Mass is density times volume. 13.6 gram, what happened there? Per mil times 10 mils. 10.0 mils. And the answer would be 136 grams. Last one, calculate the volume in milliliters of a liquid that has a density of 1.2 grams per milliliter and a mass of 5 grams. Rearrange an equation. Volume is equal to mass divided by density. Mass is 5.00 grams. Density is 1.20 grams per milliliter, whatever that comes out to be. 4 something. Questions? No? You could all do that? Okay. I hope so. So what's about specific gravity? Specific gravity is the ratio of the density of the object in question to the density of pure water at 4 degrees Celsius. Anybody remember what I said the density of water was? It happens to be at 4 degrees Celsius. 1 gram per milliliter. So I'm going to compare the density of a material to the density of water. So let's say in the previous problem, what was it? Mercury was 13.6 grams per milliliter. To compare it, I would divide it by the density of water, 1.0 grams per milliliter. So I end up with what? 13.6. No units. The grams per milliliter cancel. So specific gravity is unitless term because the 2 units cancel. So it's the same number, there's just no units. So that's often used, like it says there, in the health industry to test urine and blood samples. So when you go in for your physical, and you pee in the cup, and you get your results back, they have a specific gravity listed to there. When there's a normal range in which it should fall into. And if you have some kind of disease or some kind of organ injury, and let's say you're excreting excess protein, and that your specific gravity is going to go up. So if it exceeds that level, they know something's wrong. Or if it's below that level, it's something wrong. Questions on specific gravity? Density. Okey-doke. All right, that was the end of that.